In some recent videos, I've been looking at fake UV germicidal lights being sold on eBay, and they work. They're just ordinary disco-style ultraviolet lights. And I thought, how do I prove that though? And it turns out that I could buy a meter that measures UVC energy, but that would cost in the region of, it would be £700 plus VAT. It would be very expensive to disprove a cheap disco LED light. So instead, I've got a sensor from Adafruit, and it's based on the UVA S12SD sensor chip with a little op amp to just buffer that up. And I've rigged it up to a 5-volt supply, which is a USB power supply, and my meter to measure voltage. And the voltage coming out of this will depend on the level of ultraviolet exposure. However, it's worth noting that it doesn't go down to the far UVC spectrum. It does have sensitivity to the 254 nanometer mercury peak, but it's not super mega sensitivity. The range of LED sources of ultraviolet UVC energy tends to span 260 to 270 nanometers, so it does detect that range. But I'm expecting the common near UV LEDs to be in the sort of this area, and it's got very low sensitivity to that. I mean, it will still pick it up, but you can see it's actually even just picking up the light from these lights up here. So it does have sensitivity to non-UV wavelengths. However, its peak sensitivity is to UVC and, well, not UVC, UVA and B, but it does pick up that single wavelength from the mercury lamps that is of interest. So let's start off this test with an actual high power UVC lamp that this is claiming to be equal to. I'm also going to use a piece of glass. Now, if I put a bit of glass in between a source of UVC and this sensor, this will block the UVC and the sensor will go way down, the voltage will go way down. So let's start the test with the scariest lamp of all, the one that I'm not going to use for too long because this can burn my skin and eyes. It doesn't matter that it's in a lovely pink lamp holder. So as you can see, holding it about 4 inches from that thing, it's pretty much best part of a volt. Here's a piece of glass, slide it in, boom, straight down to 25 millivolts. 1 volt, 25 millivolts. The glass is blocking the UVC line completely. I'm going to turn this off because this is just freaky. I don't want exposed to this. This is not good for skin or eyes. I could have tested there, but I'm not going to test that right now. I could have tested my glasses for blocking the UVC with this lamp, but that would involve taking my glasses off to do it, and that would expose my eyes to its energy, and that's not a good thing. Right, I'm going to put this out of the way. Let's take a look at a UV wand then. So this is the car mechanics light that's clearly designed to detect leaks. It does a great job of making phosphors glow, and fluorescent materials like industrial, like leak-seeking dyes, or in this case, industrial fabrics, sort of glow-in-the-dark fabric. When I put it about 4 inches from here, wow, not much. So I'm not getting much result from this, and I slide the glass in, and it makes it's just attenuate just because it's reflecting the LEDs back into themselves. This is not UVC, it is not germicidal at all, it's not causing any of the effects. The LEDs are most certainly not the correct type, and also their forward voltage is too low to be proper UVC LEDs. So this is not a UVC lamp, it's not germicidal. There is some debate whether UVA and B can have germicidal effects. It's commonly accepted that UVC is the dominant wavelength for that. That's for the germicidal effects because it does actually break up the DNA of things. Okay, let's take a look at the disco light. So this is a generic disco light. It's very bright. You can see that. I've just swamped the camera out. So I expect that it's going to get some sort of reaction here. It is. It's gone up. It's not quite a volt for the light it's claiming to compete with, but let's say it's about, let's see if I can get a wee bit closer. 60 millivolts. Okay, so not even closely to a tenth, but that's not even ultraviolet because if I stick the glass in, did you see much of a difference? Nope. Not much of a difference at all, other than me moving the light about, because it's a UVA type light. It's not even UVA, it's near UVA. It's just a disco light. Tell you what, let's compare it then. This is the one that's being sold as being germicidal. Let's compare it to this disco light, which looks very similar, and it is not sold as germicidal, it's sold as a disco light. So that one's got an annoying fan you can probably hear going whee in the background. So I'm going to plug this one in. Now while I'm doing that, I'm going to actually turn a little ultraviolet batten on. Hold on, just give me a second here. It's got a safety interlock, the other battens. I want it to warm up because the one advantage of real UVC LEDs over the mercury vapor lamps is that they come up to full intensity straight away. Okay, so this looks surprisingly similar, doesn't it? This is one that's sold as a disco light and is perfectly safe-ish. Point at that, round about the same result. In goes the glass. No real difference. Slight difference, but just because it's reflecting the light back from the light itself. Okay, so that is a disco light. The other one, this is a disco light, that's a disco light. They're all disco lights. They're very pretty disco lights, but they don't kill bugs. Next thing to test is this. Is this going to be warm enough? I think it's going to be warm enough. This is a real UVC wand. It's the non-ozone producing one. That big tube did produce ozone. The ultraviolet discharge in the UVC spectrum from mercury vapor lamps is in two peaks. It's 184 nanometer and 254 nanometer. The 184 nanometer is the one that produces ozone. It splits the oxygen apart. But the frequency we're looking for here, the wavelength, is 254 nanometer. Here it is. It's just gone out. This one has loads of safety interlocks. When you turn it on, you actually have to hold this button for a while until this starts flashing, then press it again. It's designed to be kiddie safe. So we'll let that stabilize. So let's say 70 millivolts. Here's a bit of glass. Boom, right down to 13 millivolts, 12 millivolts. Back up to 70. Right back down. So this thing is genuine UVC, unlike the LEDs. I shall turn, well, it's turned itself off. This is good. Let's bring another one in. Here's another little UV light that has another safety interlock. I push the button at the bottom of it. The little blue light lights to show it it's about to start up. That gives you a time. You stick it in your fridge or whatever. This one does produce ozone. It's about to power up. There, it's powered up. Hold it near the thing. It's pretty good. It's about, even at that height, it's about 70 millivolts. Put the glass in. Boom, that is UVC because it's blocking that wavelength through the glass. So the result of my test is, I think that's a fair enough test. I'm welcome to other people's contributions here scientifically, but I would say that that fairly conclusively proves that these are not putting light out in the germicidal region. And I don't think they're even putting light well down into the UVA spectrum. I would say that these are just basically ultraviolet disco lights. Now, there is one other test that's worth showing here. I'm going to bring that other wand back because it is quite interesting. Let's bring this bit of fabric in and just wedge it under that sensor just to keep it pinned down. And also, let's bring an LED in because this contains phosphors as well. So I shall turn this on. I should have turned it on before. And I shall compare it to this ultraviolet light, which is designed to make things glow. Let's turn the light off. And you can see this one. I shall take the sensitivity off a little bit. This one is making both those phosphors glow. This one has very little effect. This one makes everything glow really brightly. The UVC has very little output in the spectrum that makes those phosphors glow. So it's interesting stuff. Watch your eyes, the light is coming back. Pow. So I think that's reasonable enough. I think I can safely say that I have done reasonable scientific research here. I wish I could find a proper UVC sensor, but as I say, spending £1,000 on a meter, which is the reason the meters are so expensive, is because there really are a specialist purpose. They're designed for food processing plants to monitor the output of the ultraviolet lights for making sure they're effective for sterilizing and in various other things, like sterilizing of hospital rooms, the huge pillars of the UVC lamps. Another thing that's worth mentioning is although you can see the blue light coming through, that's just because of incidental wavelengths. Real UVC is invisible, as is most of UVA and B. But it's interesting to note that blue glow is because of other peaks in the mercury spectrum that gives it that characteristic bright blue glow. However, it's possible for the inside of the tubes, the glass, the quartz material they're made of, cheaper tubes, can actually degrade on the inside. They can change chemical state slightly with the exposure to UVC, and it means that they actually start blocking the UVC, but they still look lit. That's why you really need something like a proper UVC sensor to monitor those tubes and their output, or just routinely change them every so often on a regular basis, because you can't just purely judge their output on the fact they're lit up. Interesting stuff. Right, and that concludes that. I think I've resolved that to the best of my knowledge. But as I say, comments are always welcome down below in the description, in the comments area, and let me know what you think of this test.